Section 12.6 is on binomial expansion. So we're taking binomial terms, which are expressions that have two terms, and we're expanding them out based on the exponent. So, for example, a binomial looks like x plus y, and the exponent, as you can see, goes 0, 1, 2, 3, 4, 5. They're increasing in an increment of 1, and we're going to see what happens when we expand these out. Just as a note, remember that anything to the 0 is 1, so x to the 0 is 1, and y to the 0 is 1. So anything to the 0, even if it's two terms, x plus y, that's always going to be 1. But we can write it out using x and y terms by saying that's x0, y0. So 1 times x0 times y to the 0 is still just 1. So we're just kind of adding in some placeholders there so we can see what happens in these next ones. Anything to the 1 power is just itself, so x plus y to the first is just going to be x plus y, basically. It's going to be x to the first plus y to the first. And what we can do, the coefficients, obviously, are just going to be 1 and 1. And again, we can add in these placeholders, y to the 0, x to the 0. Because again, those numbers are just 1, they're just holding in a place so we can recognize a pattern. X squared y squared is going to be, or x plus y squared, sorry, is going to be x squared plus 2xy plus y squared. That's what happens when we FOIL that out. Again, adding in some placeholders. This is a coefficient of 1. This is a coefficient of 1. Adding in a placeholder of y here is to the 0, and y here, or an x here is to the 0. These are both to the 1, x to the 1, y to the 1. When I do a trinomial expansion, I'm going to have x cubed, and then I'm going to have 3x squared y. I'm going to have 3xy squared, and I'm going to have a 1y cubed. Adding in placeholders, that's y to the 0, this is y to the 1, this is x to the 1, and this is x to the 0. Expanding the rest of these out, this is x to the 4th, y to the 0, plus 4x cubed y to the 1, plus 6x squared y squared, plus 4x to the 1 y cubed, plus 1x to the 0 y to the 4th. To the 5th, we have x to the 5th y 0, plus 5x to the 4th y to the 1, plus 10x cubed y squared, plus 10x squared y cubed, plus 5x to the 1st y to the 4th, plus 1x to the 0 y to the 5th. So a lot of these adding in placeholders every time I see a 0 exponent, but if you multiply these all out, these are the expansions that you will get. And what we want to do is kind of look at what kind of patterns are happening here. If we look at the first term in every sequence, so notice we're looking at our exponents, 1, 2, 3, 4, 5. If I look at the first term, the exponent for x matches each of those. If I look at the last term, the exponent for y matches the original exponent. So the first term is always x to the n, whatever n being the exponent in the original expansion, and the last term is always y to the n being the term in the original expansion. If we notice the number of terms, when n is 0, for n equals 0, I had one term in my expansion. When n was 1, I had two terms in my expansion, this being one term, this being another term. When n is 3, I had 3 terms in my expansion. When n is 3, I had 4 terms in my expansion. So there's always one more number of terms than n. So number of terms is always n plus 1. So if my expansion was x, or if my binomial was x plus y to the 8th, then I would have 9 terms in my expansion, n plus 1. if we look at the pattern of the exponents for x, in the first one I go 1 and then 0. The second one I go 2, 1, 0. 3, 2, 1. 4, 3, 2, 1, 0. I forgot this last 0. So I'm always starting with n and I'm decreasing by 1 every subsequent exponent. So for subsequent x exponents after x to the n, the first one being x to the n, the next one always decrease by 1. They decrease by 1 at every term. If we look at the y exponents, notice I go 0, 1, 2, 3, 4, 5, 5 being n. So the y exponents increase by 1 for every term. The other pattern we want to notice is what's going on with the coefficients. This is a very, very popular pattern that we're gonna look at. Notice on the outer edges, I have a 1 coefficient on all my outside terms, and on all my last terms, I have a 1 coefficient. So what we end up doing is we end up developing something called Pascal's triangle. So the coefficients form something called Pascal's triangle. And this is a very, very common pattern that we see a lot in geometry and a lot in algebra as well. So notice the coefficients, looking just at the coefficients for getting x and y. For the first term was 1. For the second expansion was 1 and 1. For the third expansion, they go 1, 2, and 1. This comes from, we're going to have all along our outside 1s on both of our edges. So the first term always has a coefficient of 1, the last term always has a coefficient of 1. And where this 2 comes in is 1 plus 1 equals 2. So what we're doing is we're adding up the previous terms that it sits between, and that's where we get this 2. So on the next one, I'm going to have 1. These two terms add to 3. These two terms add to 3, and I end with a 1. On the next one, these two terms add to 4. These two add to 6. These two add to 4, and I end with a 1. And I just keep doing that. This is going to be 5, 10, 10, 5, 1. And I'm always ending in this symmetrical pattern. 6, 15, 20, 15, 6, and 1. So again, along the outside edges, always 1s, and then I'm just adding up the numbers in between. That's 6, 15, 20, 15, 6. So the first row corresponds to x to the 0, the second one x to the 1, the third x squared, the fourth x cubed, the fifth x to the fourth, the sixth x to the fifth, and the seventh row corresponds to x to the 6th, or the binomial expansion. This is the first, I just wrote down the first term, but this would be obviously x plus y to the 0. This would be x plus y to the 6th. So these coefficients are what happen in front of the x and the y terms, and we're going to look at the pattern for this and look at how to use this in an expansion problem. So for example, use Pascal's triangle to expand the following. So I have x plus y to the 8th, and what I'm going to do is I need to find this 8th coefficient, that's n equals 8 in this case. So I'm looking for the 9th row of the triangle. Because notice in the triangle, my 0 coefficient is the first row, my first coefficient is the second row, so my 8th coefficient is going to happen in the 9th row. And if I locate the 9th row, which I've expanded out for you here, it's going to be this. So these are going to be my coefficients. So what I'm going to do is I'm going to come down here and write out my coefficients. So my first term is going to be 1, then 8, 28, 56, 70, 56, 28, I'm going to come down to the second row, 8, and 1. Those are my coefficients, and then I just need to fill in my variables. So remember, I'm in the 8th term, So my x value is going to start with an n with the same n. So this will be x to the 8th, x to the 7th, x to the 6th, x to the 5th, x to the 4th, x to the 3rd, x squared, x to the 1, and x to the 0. Remember, my y's are going to go in opposite order. So they'll start at y to the 0, y to the 1, y to the 2, y cubed, y to the 4th, y to the 5th, y to the 6th, y to the 7th, y to the 8th, and all these terms are adding together. So I'm just going to add an addition sign between them all. What I'd like you to do now is go and do part A here. Do that one. See if you can expand that out using Pascal's triangle, and we'll do the second examples in class tomorrow. Okay, so what we're going to look at now is a definition for the binomial theorem. And your book has how this is derived, but I'm just going to give this to you and we'll talk about how to use it. So when you have a binomial, x plus y, and you've raised it to the n power, it is equivalent to the sum of r to the 0 to the n of n factorial over r factorial, n minus r factorial, x to the n minus r, y to the r. So n obviously is whatever number you have here. R is one less than the term you're looking for. So I'll show you what this means. Otherwise, you're just plugging in n and r. So what we want to do is we want to find the fourth term of an expansion for 2x minus 3y to the 6th. So instead of writing out all 7 terms for that, I just want to know the fourth term. And this formula gives us an easy way to locate just that term. So what we need to know is that n in this case is 6. That's the value it's being raised to. R in this case is 1 less than the term you're looking for. You're looking for the fourth term, so R is going to be 3. So what you're going to do is you're going to write out this summation formula. So the sum from R equals 3 to 6, where R is 3 and n, is going to be n factorial, so 6 factorial over r factorial is 3 factorial, n minus r factorial, x to the n minus r, y to the r. So I'm just going to simplify this out. This is going to be 6 times 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. 6 minus 3 is 3 factorial, 3 times 2 times 1. So these all cancel. 6 and 3 make up, 6 and 2 make up 6. So I'm left with on the top there is 20. X is going to be, my x term, I forgot here because we didn't talk about this, x term is going to have a 2 attached to it in the front. You just keep these coefficients out front, and negative 3y. So when I do that, I'm going to have 2x cubed and negative 3y cubed. So this is going to be 20 times 8x cubed minus times negative 27y cubed, which is going to be negative 4,320 x cubed y cubed. Okay, so I would like you to try the next one on your own. We will go over this some more in class, so don't worry if you didn't get it too much. I know this is a little bit rushed video, but notice this is your answer that you're looking for the 5th term. So try that out. N in this case, n is going to be 7, and the term you're looking for is the 5th term, so r is going to be 4. And please remember to keep the numbers attached to your x and y's. Try that out. We'll see how you do.